Today we're going to be putting through their paces the cheapest 4,000 watt inverter I could find on eBay and the quality 3 kilowatt inverter. I've removed both their names to save me being sued. We will be doing, amongst the simple tests, we'll be doing a full thermal scan of the inside working components when both of these are under load, so we can see the heat that's being generated. We will put them both on the oscilloscope so we can see the sine wave at idle and at full load. Plus we'll be doing all the basic other little tests that we do when we test these little inverters. So stick around and let's see who comes out on top. Got a 5 kilogram scale here, maximum 5,000 grams. Let's try the little fella first. About 1.7 kilos, 1,700 grams. I don't know if you can see that, you probably can't, but that's what it says. Let's try the fatty, the big girl. And it's overloaded the scales, so we don't know what this one weighs, but it weighs more than 5 kilograms. So clearly this one is going to be no good if you want to put an off-grid system on your scooter, but this would be ideal if you're building a backup system or a power supply system on your bicycle or your scooter. So this one comes out on top for lightweight. So we can see just by looking at them, the physical size is substantially different. I don't quite understand how they can claim this is 4,000 watts, but that's what they say. I mean, they're both fairly similar on the outside. This one doesn't have a remote, but this one has a remote option, little RJ45 socket. It didn't come with a remote, but it's got that option. Or maybe it did, I'll have to check. It may have come with a remote. On the back end, we've got these horrible screw-in terminals. When we do the thermal scan, I've already done a thermal scan on this one, just take a note at how hot these terminals get. It just goes to show that you can't do them up tight, or they just don't have enough meat to clamp up around the terminals. So that's a bit of a heads up there. This one's got the nice hidden terminals, they're protected, and they look fairly chunky. I have to take these covers off to screw them up. This particular one, well, not this particular model, but this type of inverter, the next model up, comes with a automatic transfer switch, so you can hardwire this inverter. So for heavy duty loads where you need something more than the 15 amp sockets on the end, you can hardwire it. All right, well, let's pull them apart and have a look at the components inside. Okay, they're both opened up. Let's have a look at this one first. As you can see, the DC side is quite robust. We've got solid steel bar plugged into the bridge rectifier, both the positive and the negative. Not relying on wires, they've got this nice solid piece of one-piece steel all the way back to the lugs. That's pretty sweet. Probably take some good current on there, as you would expect. The bridge rectifier's got plenty of cooling capacity. Lots of capacitors there, and lots of 40 amp fuses on the bridge rectifier side. Then moving up into the AC, we've got some toroidal coils, more cooling, some big smoothing capacitors just up here. A couple more toroidal coils, don't know what they're doing, more smoothing capacitance. No earthing, which is normal. The AC out is paralleled up off just 2 pins. I'd like to see individual feeds to the back of those, but I guess it's only about 12 amps when they're pulling their rated current, so it feels like 2.5 mil. So that's good for about 26, so it probably doesn't matter. You're still relying on those pressure lugs there to take 12 amps. But yeah, a lot more solid chassis. I would expect that this is not going to heat up too much, but we'll find out. Over to the little chap here. Just got some flex feeding the DC side from the lugs over to bridge rectifier. It's only got one smoothing capacitor compared to the other one's multiple. And what have we got in the way of fuses? Can't see them down there. Oh, you probably can't see them. I can. There's also 40 amp fuses on the DC side. And then moving up to the AC, we've just got the one smoothing capacitor, one toroidal coil. Again, it's paralleled up on the AC side, so relying on one feed. This particular one, I've done an earth modification to the back of these because I was introducing an RCD. So interesting to note, you can't use an RCD on these unless you do some external earth modifications. And I've got those in another video if you want to have a look. Alright, so yeah, not much cooling capacity on these. There's no heat sinks that I can really see. Not a lot of cooling capacity in that. Whereas this one's got big cooling fins. So I think we'll do quite well with this one here when we put the thermal scan on it. Alright, well let's put them on a test bench and see what happens. The test bench we will be using was this bench here. It's one I set up previously for some live earth testing. If you want to see that video and see how different earth practices behave when we put 240 volts onto various components and simulate fault modes. I've got a fault mode here. I can put it into fault mode and do various things, bring the safety switch in and out, but that's not the test we're doing today. You can see that test at the end of this video if you want to stick around. What we'll be doing today is loading up this inverter and the other inverter, and we'll know when it's powered up because we'll have our test light on. We'll put on an oscilloscope. We'll do an efficiency test with the volt and the clamp meter, and we'll be loading it up with a 2000 watt heat gun first up, and if they can cope with that, we'll be putting a 1600 watt heat gun on it. So we'll be overloading both inverters. Or we won't be overloading the little one apparently because that's what it says, 4000 watts. So that one should be able to cope with it nicely, and I hope that the big 3000 watt should be able to as well because it will have a peak current that should be able to run 3600 watts for a short period of time. And powering this up, we will be using the iTech 200SS battery. Big power in a small package. It's only 150 millimeters tall and it's 400 by 500. What I really like about this is it's got this state of charge app that connects straight to it. You can see all the individual cells, and what's pretty cool is you can control it remotely. Right, we'll get this first test underway. We'll start it up. Anybody else using soft starters on their inverters and their batteries? Okay, so we are powered up now. You can see nothing on the oscilloscope. Starts up, a little bit noisy. Oh, quite a nice sine wave. A few little steps in there, but you know, not bad for a cheapie. It's pretty good, pretty stable. It does have a nice little screen on the front of this thing, so it's quite trendy. See the voltage and you can probably see the current as well. Alright, but we'll take that lid off for this test. So what we're going to do is put the thermal scan camera on this, but first we'll put on the 1600 watt heat gun. We'll see what the oscilloscope does, and we'll do a current and a voltage test, and we'll look at the efficiency of the in and the out of this and see what the efficiency rating is. And then as we load it up, we'll see what the oscilloscope does, we'll see what the temperatures do, and we'll see how long it can run on overload. So we should expect that this will do 4000 watts fairly easily. That's what it says, and that's what the marketing said. Alright, so let's take a note of the starting current and the oscilloscope when I turn it on, which I will do now. Oh, well, 30 seconds in and it passed out. And it's making a funny smell, which is interesting. So we got to 211 amps. We'll work out how many watts that is. And yeah, you saw the sine wave collapsed a little bit, but it did start those loads, so it was able to start. But I want to see this run a bit longer because I want to see how hot it gets. So we're going to have to remove one of those loads, I think, because it only ran for about 30 seconds and then it started to smell. All right, let's try that again. Alright, so thermal scan, you can see the temps here over 100 degrees. Just to note that this camera is not too accurate with its exact temps. It's probably about 10% over. When I put a heat gun onto it, it seems about 10% over, but note that I couldn't actually hold my fingers on the positive terminal here on the back of this inverter. It was too hot for me to squeeze or touch. Also interesting to note that my isolator's got a bit of heat going on around it there. It's very good, these cameras, to check your connections and whatnot. Also looking at the battery terminals here, you can see they heat up and the connections of the fuse. So I'll put a link to the camera I use in the description. They're very good if you're serious about monitoring your temps. And we have cut out. So 3.5 minutes at 1476 watts. So are you a 4000 watt inverter? Look at that, it's got an ER4 code. Well, that's kind of handy. I don't know what ER4 is meant to mean, but that's what it's telling us, probably over temp, overload. 4000 watts, 3.5 minutes. Yeah, you be the judge. Right, let's move on to the other one. So exactly the same test as we did last time. We'll turn it on, see what the sine wave does. We'll put a load on it, check the efficiency factor of it, check the voltage and the current. Then we'll load it up to its peak output. Again, we'll see what the sine wave does, see if the voltage and the frequency change at all, see if it drops off. And then lastly, we'll let it run at its rated output for 10 minutes. We'll let it heat up and we'll put the thermal scan camera on it and see what the temperatures tell us. All right, let's go. So let's just turn it on. Oh, well, that's an interesting sine wave. Is that a pure sine wave? It's supposed to be a pure sine wave inverter. What do you think? I'm a bit surprised. All right, well, regardless, let's get a load onto it. All right, let's see what the standby current is. 1 point, yeah, just over an amp. So going into the thermal scan here, you can see the temps aren't as high as in the smaller unit. Again, consider this is about 10% over than the actual temperature. And then we load it up with the second heat gun, and it runs for about 30 seconds. And then, as we can imagine, it cuts out. Right, a little bit surprising there. We got the rated output. We got 250 amps on the input, and we got 3000 watts coming out. But it only ran for a few minutes at 3000 watts. And then we loaded it up. I got 350 amps out of it. That's approaching peak output, and it ran for maybe 30 seconds. As expected, wouldn't expect it to run too long. The sine wave was quite surprising. I might actually be in touch with the manufacturer about this, because I don't think it's running as it should be. What do you think?